We'll look at it now. So number 6. Okay, well it doesn't matter. I'm going to do it now. Yeah. A racing car goes around a circular curve as fast as it can without skidding. The radius of the curve is 50 meters and the road is banked at 20 to allow faster speeds. The coefficient of static friction between the road and the tires is 0.8. So let's draw this first. Okay. So what's the mass of the car? Or we don't know, so we don't need to know. Okay, so here's my first force, mg. And then here is my second force, reaction. Okay, but there's also a friction force. Now this is the thing, which way do we draw the friction force? Left, right, up, down, centre?
Right, left to right. Left and centre is the same.
Or do they actually say?
Left.
Friction force this way?
Yeah.
Well, let's look at the car from the top to help. So here's the car on the top of the road. So when I'm looking at it from the top, it's going around like this, isn't it? So there are some forces.
And the left.
Yeah, you see, I think I should put my friction force,
Left.
I don't know, to the left.
Yeah. It goes like that. The friction goes to the center of the circle.
It's on the direction of the force.
No. I don't know if I should do it this way.
Why?
Well,
yesterday you said that.
I know, I said the force for making it go in a circle.
Yeah, it goes in the circle, so the force goes
You
towards
say
the center.
Yeah.
Friction is what
So,
causes the force.
Center.
Yeah. Don't know. This seems to be a bit more difficult. You see, the reason for that is if I was to break this mg up into this direction, then those two would cancel. They have to be equal. And then I have in this direction here.
But you also
Which
can
is
resolve
equal
R.
to F.
You have to resolve not mg but R. You can resolve R.
Yeah. Yeah, you know what? Actually, I think looking at the other way would be more helpful. If I resolve the or, so the or is this way, and the or is this way. So let me remove, oh well, not remove it, but this one here, this angle here is 20. So that means this one here is 20. Can you see why? It's that Z shape. 20 and 20. So this angle here is 20. Yeah? Can you all see that? Yeah? So I want this angle here. No, I'll draw it again just to make it a bit clearer. You don't need to remove yours. I'm just drawing it again to make it clearer. Okay, so if we look... Hey, no, just look. Okay, so firstly, mg, and then here I'll just do ... Or, so I can break it up into this direction and this direction. Okay, now let's try and find the angle. So this angle here is 20. So if I try and draw it, it's like the... Sorry, I should have put that point down here. It's easier to draw. But this one here is 20, which means this one here is 80. Or in other words, this one here is 20. So that makes this here or cos 20, and this one here or sine 20. But I haven't put in the friction yet. I really think I should put my friction in this way.
It goes.
Because I don't know why. I don't even know if I should put it in this way.
But it should go towards the center.
No,
of the circle.
no.
But you said it yesterday.
No, I didn't say the friction should go towards the centre. I said the force that makes it go in a circle goes towards the centre. And if you look here, R cos 20, I know R cos 20 must equal mg. Alright? But the R sine 20 is could be the force that makes it travel in a circle. Okay? I think the reason I said the friction must go up, I think, because if it didn't, the car would want to slide down. But I'm not even sure about that. We need to think about this carefully. I remember doing a problem like this a long time ago. Okay, I'm happy with the R and I'm happy with the mg. The only problem is what way to draw the friction.
If you draw it like that, then you have to resolve it again. The
Yeah,
friction.
you're right.
And one of the forces would be in the same direction as r cosine 20, another one would be
Yeah, which is okay.
in the opposite for r sine 20. So mg would be equal to r cos 20 plus the resolve.
I think maybe I should do the friction towards the centre, but let's see what you did. So which way did you draw the friction? To the left? And you got the wrong answer.
Yeah.
See? You did it to the right?
Right, right.
And did you get the right or the wrong answer?
No, I didn't finish.
Okay. See, what I'm doing is I'm picturing it like this. I'm picturing it like this is the road and this is the car. So if I just let go, what should happen to the car? It slides down. So there must be some, I feel like there should be some friction force from the tyres keeping the car from sliding down. Okay? I think I'm going to do the friction going up the road. It's a bit like, do you remember when we put the block on the wedge and it slides down? Which way is the friction? It's going up.
Okay, let's do it.
We can try it. We can try it. I think in the exam you might get the information in the question to help you that the friction is going up the plane. Okay? Let's see what happens. So I'll draw the friction going this way. So it's mu or, what's the mu? 0.8. So I need to resolve it. Whoops. So I have it in this direction. And I have it in, yes?
Aren't you meant to resolve the weight?
No.
Because the weight is,
Yeah.
it's not
No.
all directly going down.
No. What you resolve is your choice. I chose to resolve the or because I want to put everything in this x and y system.
Why isn't the car also falling now? It's not. It is over force.
No, but I know for when we did the block and wedge we resolved the weight, but here I think resolving the weight would make it more difficult. You can resolve whatever vector you want and you don't have to resolve it. And I'm choosing to resolve the or so I can make it in the y and the x direction. And the weight is already in the y direction. In this situation it's easier to resolve the or. If you want you can resolve the weight, that's fine. But I think it'll make the problem longer and more complicated. It's just my way of trying to do it quicker in this case. Okay, who knows what this angle here is? It's 20. So this would be 0.8 or, because that's the friction, mu r, cos 20. And then this one up here would be 0.8 or sine 20. So I get this equation.
mg
0.8 or, sine 20 plus or cos 20 must equal mg. Because I'm saying this up force plus this up force must equal this down force. Now, this is travelling in a circle. So which way does the force act? To the centre of the circle. So that means there's a force going to the centre of the circle, and it's made up of or sine 20, and then what do I do with this? Plus or minus? Minus 0.8 or cos 20. But this is a circular force. Now, do we know anything else? We know the radius, don't we?
Yeah.
So which formula should we use? Do we know the V? No.
We know R, we know angle, and we know mu.
And they want V?
Yes.
So then we should use the one with the V in it then.
MV squared over R.
Yeah, well we use mv squared over r. So we have mv squared over r equals r sine 20 minus 0.8 or cos 20. Okay, so we have this equation. And then we have this one here. I should get or from this equation and then sub it into that one. So we can do that. This would be 0.8 sine 20 plus cos 20 or equals mg. Can someone type this in, please? What do we get? 0.8 sine 20 plus cos 20.
We can do it later.
No, do it now. Because I want to make this smaller.
It's 1.21.
So it'll be mg over 1.21. Yes? Yes? Are we sure? Okay. No.
I go 1.14.
Yeah, you have 0.8 sine 20 plus cos 20, degree mode. Yeah?
But it's 1.
Okay, what did you get? Dana, what did you get? 1.21? Okay. Yes, I'm going to continue. So, putting that in here now, I have mv squared over 50 equals mg sine, mg over 1.21 sine 20 minus 0.8 mg over 1.21 cos 20. Okay, so I need someone now to tell me this one, sine 20 divided by 1.21, and then this one here, 0.8 multiply cos 20 divided by 1.21.
1.5.
1.5?
That's
The first one?
the first one, yeah.
Exactly 1.5 or
Yeah, no, 1.5. Right.
1.55?
Yeah, 5532.
Okay, 55 mg. Is that right, Dana? No? What? Ah!
Put in.
Give me a calculator.
That feels good.
Sine 20 divided by 1.21. Yes! 0.28 mo.
Did you multiply?
0.28 mg. Don't worry, I'll do this next one myself. 0.8 times cos 20 divided by 1.21 minus 0.62 mg. Oh, sorry, mv squared. Now, all those m's cancel. So hang on. 0.28 mg minus 0.62 mg. Dang. That's bad. Yeah. Not cool.
So did you
Did I what?
up there? Did you actually substitute the first equation into the second one?
Yeah.
Oh, but it's over there. It's mg and over there it's mv square over 50. How to choose?
What? No. This is right. I got, from the first equation I got, well, maybe,
I mean the one you made in the
Hang on.
circle.
let me check this. Yeah, it is 1.21 equals mg. What's wrong, Tanish? No. Alright, so that's wrong, because here I get a negative number, which is bad. So, bad, Stephen. Bad.
I think it's just somewhere
You think it's just an algebra mistake?
not the algebra,
The sign?
the sign mistake. I'm pretty sure.
So why don't you try out?
No! Why don't everybody just relax for a minute? Right. This is fine. This is good. This is real life. Mistakes happen in real life, and we need to know how to fix it. So don't say anything. I don't need anyone to say anything. I just need people to listen. I did the friction going up the plane. Yes? And this gave me a situation that is ridiculous. So I think I must have drawn it the wrong way. I think when the car's driving, it has its friction force driving it forward, yes? But the wheels are turned, so it can go around in the circle. So then the friction will do going down the plane. But you said into the center didn't work. But I don't think it's into the center. I think we should do it, look, I think we should do it this way. Because the wheels are on the road. So that means I just need to change my plus and minus here. So instead of having plus and plus, what should it be? Minus and minus. So where are those pluses? The 0.8 or cos 20 and sine 20. You see there? These ones. 0.8 or sine 20. Isn't it? What did I say? So instead I get or cos 20 equals mg. So that's fine. But I don't have the 0.8 up anymore. I have it down. So that should have been a minus now. So just change that to minus. And then what about the other one? Yes. Instead of minus here, it's on the other side, so it's a plus. So if I make that a minus and a plus, that means I need to change this number here. So I have minus 0.8 sine 20 plus cos 20. So that's 0.666 instead of 1.21. And instead of a minus, that's a plus. So change that to plus, and then this here and this here, change it to 0.666. And let's see what we get now. Alright. Sine 20 divided by 0.666. That is 0.51 mg. Plus 0.8 times cos 20 divided by 0.666. Here? It was negative, it's positive now. Which denominator? No, I think it's okay. 1.13 plus 0.51, so in total that is 1.64 mg. And are we to take G to be 9.8 or 10? 10. Times 10 times 50. What's the answer at the back?
20.
Boom. That's how we do it. So 28.6 is what you get for V.
I don't listen to anything from
From where? The last bit I
No, I just saw it by myself.
a board question. Okay, so it's okay.
So, where did you, can you show the sketch again? Where was the...
Yeah, so the friction, so this was the complication. If we look. So if you look up here, the car is going around the road like this, okay? And we have our weight, we have our reaction, and the problem is the friction. I tried this, no good. You tried this, no good. It's this. Now the reason it's this is because if you think about it, which I didn't do, when the car is on the road, what did I say the friction does? Drives it forward. Yeah? But he is turning. So the wheels are turned left. So instead of going this way, the friction force is actually this way. Which is what helps him go
So it
in
goes
the
down
circle.
the plane.
So then
Yes.
how could you use
Yes.
the angle 20? Because the angle 20 is like for the result for the x-axis. I mean,
It's the result of reaction.
So,
Yeah.
so what?
but like the angle you said is like if you resolve to get 20, it's like this, like what we did this day.
No. The mistake was you should draw the friction going down the plane,
Yeah.
not just going in the middle of the air. Yeah.
Do you have a pen to draw before here? Where exactly was it going?
Which now? The friction?
Yeah.
Uh,
So if it goes down the plane, we have to resolve it.
yeah. So, can we just use our imagination? This road's at an angle, and imagine it just goes around in a big circle. Okay, and then here's the car here on top of it. Okay. So, the weight goes straight down to the earth.
Okay.
Do not resolve it.
Okay.
The reaction is perpendicular.
Yeah,
Resolve it.
Friction.
Yeah, I resolved it into the two, horizontal and the vertical. Yeah, I didn't resolve it into the plane and the
Yeah.
perpendicular to the plane. I resolved it into the absolute horizontal and the absolute vertical.
Yeah, that's what I meant.
Yeah, and then the friction goes down the plane towards the center of the circle
So resolve it.
and resolve it. Did I also do that horizontal and vertical?
No.
Absolute.
So F would be
But you use the absolute
result
horizontal.
horizontal.
Yes, yes. And the F that makes it go in the circle
It
is
would be the result friction.
the resolve
plus-
friction plus
plus
the
resolve.
resolve
Yeah. Reaction.
reaction, yes.
Okay.
Resolve reaction plus resolve friction.
Okay.
Yeah. That was difficult. Yes, true, that was difficult. That is more difficult than the plane because I think with the plane we don't have to worry about the direction of the friction force. We did here. But this is good because, you know, it's the last question in the homework. So if you found the last one a little difficult, that's okay. And I hope you all can see what to do now. What's wrong? Is this question okay? No, I shouldn't really say that. How do you feel about this question? Sorry. Not how do you feel. How do you feel about the question? Yeah?
Good.
Yeah. Yeah. Okay. We'll go on to the next topic now. Please, I would recommend people try to do the question again themselves tonight if you didn't get it, just to make sure you understand it, okay? So you can, before I even give you the homework, you can add that one to the homework to do that again. What? What?
7 still.
Oh yeah, it's gone. Alright. So I'll give you the questions later today, but as a minimum, I would like people to do that question again, and I'll check it tomorrow, okay? And try to do it without looking at the video or my answer. But I will check it next time, okay? I do feel it's important. All right, we'll continue then. This is this. Okay. Now,
This is 11, isn't it?
yeah, we're going to page 60 and 61. So I'm skipping a couple of pages that aren't relevant for the syllabus, but they're there if you want to read them. So 60 and 61. Okay. So back to our main man, Newton.
What is the topic?
Well, it's Newton's law of gravitational attraction. Gravity. Sorry. So, we know that if we have a mass here, and then a mass here, and they're separated by their centers, a distance r, there is actually a force that pulls them together, and you know what? That force is called gravity. Well, no, don't do that. I deliberately, what? You know gravity, don't you?
This is gravity.
Yeah, this is gravity, yeah? What's wrong?
Is it with a big G before the...
Yes.
Oh.
You have to say it from very...
Yeah. So there's a force that pulls these together. Gravity force, gravitational force. So example could be sun and earth, earth and moon, sun and Mars,
So
you know.
any two objects in the world.
So after
Yeah.
gravity acts vertically. So
But we're in outer space now. There is no horizontal and vertical. Yes?
yeah.
Hey, all right. So the force between these two is given by this formula. You multiply this constant g by the masses and divide by the distance squared. And g is a constant, and the value of the constant is 6.67 times 10 to the minus 11, and it's your job now. I want everybody to tell me the units. So I want people to give me the units for g. I want you to work out the units. And you can get the units from this formula. So give me the units for g. You know what to do? No, you look confused.
Yes, I know.
Okay. Yeah, what is it? Nearly. Maybe.
Do we have to make F each kilogram meter per second?
No, you can leave them as newtons. It's fine. So you can rewrite this as g equals f(r) squared over mm. So the units for g are the same as the units for this. So what's the units for f? Newton. Distance, meter squared. Kilogram squared. So that's the units. The units are Newton meter squared per kilogram squared. That's the unit for G.
Cubed over second squared kilogram.
You can change it around, yeah. Kilograms, meters per second squared. Yeah.
Can you go up?
To what? My diagram of sun and earth. nothing exciting. Okay, you got that? Yeah. So, let me give you a small example to do for me. Can I scroll down?
Yeah.
Yes? Okay, so here, this is what I want you to do. So, this mass here, let's say it's, I don't know, 10 to the 10 kilograms. And then here is our rocket. Now, the rocket is not on, okay? It's off. There's no, it's not burning, it's just floating. Okay? So, it will, and we'll make it, I don't know, 5 kilograms. We'll make it small. So, this rocket is being pulled towards this planet. I would like to know the force, please. So what else do I need to tell you that I haven't told you? Distance. So we'll make this separated a distance, I don't know, 10 to the 6 meters. Something like that. So tell me the force, please. I want the force.
Is it 3.335 times 10 to the power negative 6 meters?
I don't know. I don't have my calculator here. What else did you... Someone else get an answer? Same thing? Great. So you put the numbers in the formula and out comes what?
3.335 times 10 to the power negative 6.
Okay.
Newton meters.
No, just newtons. It's force.
Oh.
I
Yeah.
got the power negative
I got the one that
Yeah.
upset.
Great. Okay, so we can continue a little bit. Yeah. So, let's take an example here. Earth and then moon.
That's not how well.
Yeah, also the Earth and moon aren't on graph paper. So it's the least of my problems right now. So as you know, moon goes around the Earth. So we can calculate the force here. Are we looking up? Yes, Dana and soon. So let's say the mass of the Earth is m(e). And then, well, actually, let's just call it big M and small m. So there's the mass of the Earth, big M. I don't want to use another circle, sorry, big M. And then the mass of the moon, small m. And then the distance between them, we'll just call it r. So, let's calculate this F here. What's the formula? F equals gmm over r squared. That's Newton's law of gravity. Right?
Mm-hmm.
Now, let's look at this one. Look there. Let's use Newton's second law. What does Newton's second law say? F equals ma. So I can put these together and I get ma equals gmm over r squared. What happens to those small m's? They cancel. So I get this result. A equals gm over r squared. Now, you know that this motion is a circle. And what force is making this go in a circle? That gravity force there. So you have a formula for acceleration if it's moving in a circle. I gave that to you in the last class. So give me this acceleration formula, please. V squared over r. So you have but a equals v squared over r. Therefore, you have now v squared over r equals gm over r squared. Okay, so what happens now? Well, that cancels that, doesn't it?
Yes.
So you get v squared equals gm over r. But this formula, wait, I'm not going to continue with this one. I'm going to stop. Because this formula, I'm trying to get to a particular formula. We don't know how fast the moon is moving, do we? No. So let's use the other formula. What's the other formula for A? But A equals, I gave you another one. There was two, wasn't there? There was.
No, just one.
No, just one.
Just one.
You gave us two false
For
ones.
M.
All right, well then just take out the M. Yeah, so what's the other formula for A? With the omega in it. No, don't look at me. You know what I'm talking about.
Oh.
You have two formulas for F, don't you?
Yes.
Yeah. So just take out the M's and they're now the formulas for A. So where are they? Here and here. Yeah, so V squared over R. No, it didn't help me. So I'll use this one. Omega squared R. Without the M. Because I want to make it an A, not an F.
Oh, okay.
Yeah? So I have omega squared R.
So why did you take out that n?
Because I want A.
This F equals MA. And F equals M omega squared R. Take out M's and do omega squared. And omega squared R is A.
Look. F equals M omega squared R. But what's F? MA. MA is M omega squared R. So the M's cancel and I get A equals omega squared R. I put that back into this result. So I get omega squared R equals GM over R squared. I can take the R down and I get omega squared equals GM over R cubed. Actually, you know what? I think I'll bring the R cubed up to the left. So I have omega squared R cubed divided by G equals M. I just rewrote it. Okay, now I have a formula for omega.
Yes, you
What's the formula for omega?
do. Which one?
Yeah, V over R, isn't it? Yeah. No, theta over T. Yeah. Yes. So, I can use that now. But omega equals theta over T. Now, if I'm talking about one circle, yes? What is the angle for one circle? 2 pi, 360, 2 pi. So for one circle, it's omega equals 2 pi over, and I'll use the letter capital T to mean the time for one orbit, one circle, period T, yeah. So I put that in there, and I get 2 pi over T squared, or cubed over G equals M. So I'm left with now M equals 4 pi squared or cubed over GT. Oh, sorry, T squared.
How many times did you solve this thing?
How many times?
Yeah.
What do you mean?
I mean, like, this is the classical thing for this problem.
Yeah.
I think almost every year it comes up in things, yeah.
No, not every year. A lot of the time, though. So what have I done? I have produced a formula. What's the big M? What's the big M?
Mass of the
Mass of the Earth. Yes? What's the small r?
Radius.
The radius between the Earth and the Moon. And the big T?
The time taken for one
The time taken for one revolution. Okay? Now, how long does it take for the Moon to go around the Earth? About 28 days, isn't it? This is the point I'm making. I can know the mass of the Earth if I know two things. The first thing is big T. Do I know big T?
Yeah.
Yeah, it's about 28 days. And could I know the distance between the Earth and the Moon? Yeah, that's not too difficult to work out using telescopes.
Why
Yeah.
did you say 28?
Huh?
28.
The Moon is roughly 28 days. Yeah. Now, this is why this example is important. The example is important because it lets you calculate the mass if you know only two things: the time and the radius, the distance. So can I get you to use your imagination for a moment? So imagine that you're looking at a planet in a telescope very far away. Everybody's listening, aren't you? Yes. So you're looking at a planet very far away. And you look at this planet and you see a moon going around it. Okay? And you see, every 5 days the moon goes around once. So do you know T? Yeah? And then it goes around and you can use your telescope to see how far the moon and the planet is. So if you know the R and the T, you now know the mass. So this is how you can work out the mass by looking at a planet. You need to see and look for something that's going around the planet. And that's all you need to know. And you can work out the mass of the planet. Okay? So when people say, this star has this mass, or this planet has this mass, how do you know that? From this formula. Okay? So this is an important formula. And the proof of the formula has been on the exam twice. Okay? Now, you'll recognize it because what will happen in the question is the question will say something like, the moon is this distance from the Earth, and the moon takes 28 days to travel around the Earth. What is the mass of the Earth? Or another example might be, the Earth is 1,000,000 meters or whatever, billions meters from the Sun. And the Earth takes 365 days to go around the Sun. What is the mass of the Sun? Okay.
Is it part A or B?
Huh?
Part A or B? Question.
B. Yeah. That formula, you would need to know how to get to that formula. Okay, so this is an important proof. There's not really any proofs in the physics exam, except this one I've seen. Okay, so this is important. And this formula has a name. I wonder if anybody knows the name of this formula.
Keplers Law?
No? Yeah.
Keplers Law?
Yes, Kepler's Law, yeah. This one is called Keplers. Now, which one is it? Is it his first, second, or third? I don't know. Let me see.
No,
It is.
right. You told it correctly.
No, I'm looking for if it's first, second, or third. It is, I believe, Kepler's. It doesn't say it in the book on page 63, I don't think. But I think it's on the previous page. Is third law, maybe?
Third law is R cubed over T squared, so yeah.
Yeah. So it's Kepler's third law. So Kepler, just like Newton, has 3 laws. And this is his third law. Okay. Now, it's stated different ways, like you said there, about the R cubed and T squared. But this is the useful way of stating it because it gives you something to calculate the mass. So that's Kepler's third law. Yes?
in the exam, instead of having the formula, can we just write according to third law, m equals to
As long as the question did not say use any verbs like show or prove, if it just said something like calculate or what is, yes. You could say by using Kepler's third law, that's fine. But this I know for a fact is not in the formula book, for sure. Okay, so that's Kepler's third law. So who is this Kepler and why do I care about him? Well, okay, maybe you don't care. But he has two other laws.
Was he Polish?
Yes, he was Polish. Yeah. Okay, so his laws are, that's his third law. So let me give you his other two.
Actually, he's German, according to the book.
Is it? It says Polish monk.
No, it's that they
Oh,
underneath it says
he's German.
Yeah.
Okay. Right, first law. Hey, guess what? First law. Planets go around other masses either as a circle or as an ellipse. Yeah. I mean, that's all I need to say about that. There's more to it, but that's all I say. So when something is in an orbit, it's either a perfect circle shape or this kind of ellipse shape. Perfect circle, yeah. Perfectly circular. But that doesn't happen. Most of the time it's like this. It's usually like this. It's not often like this. I think if you did the Earth and the Moon...
So what's the name of the shape? Or
ellipse or oval. It's not important.
You have 3 laws and basics for one.
Yeah. But look, Moon and Earth I think is pretty circular. But Sun and Earth is more stretched out. Doesn't matter. In the exam, they'll always say, assume a circle. So most of the time, 95% of the time it's like this, 5% of the time it's like this, but not important. In the exam, they'll say, assume a circle. Why? So that you can use your circle equations. That's why. So what you do is you say, oh, well, it's roughly a circle. Now, it's not, but it's not too bad, okay? So that's his first law. Second law, I'll show it to you again by a graph. Okay, so I don't know. Let's imagine. Oh, that's silly. Let's imagine that this is the going around here. Whatever. Yeah, whatever. 2 doesn't matter. And this here takes 1 day, and then this here takes another day.
So what are you doing then?
This is this can be like Sun and Earth maybe. So after 1 day goes here, then another day goes here, and another day goes here. Okay, so I'm just drawing you different days. Kepler noticed that if you calculate this area on the first day, I call it A1, it will equal this area on the second day, which equals this area on the third day.
Isn't that logical? It takes the same amount of time.
No, because maybe the planet is getting further away from the sun. So it's getting like, if I draw, I'll draw a more extreme example. So if you look here, there's the sun, there's the earth. So here is 1 day. Let's say this is January 1st, whatever. And then let's say we look at over here at June 1st. Kepler noticed that this area here must be the same as the area over here. Now, this area is very big, isn't it? But this here is very small. So to make it big, I need to do it very wide, so that this area can be the same as this. So what happens is, over here, it moves more in one day than here. It moves less in one day. Because the area must always be the same. So the area on for a day must equal the area on any other day. That's Kepler's second law. Now, does it work for if you do weeks? Yeah. Seconds? Yeah. Minutes? Yeah. So the law is the area travelled per unit time is constant. So if it travels this area in 1 second, it must travel the same area in the next second. Okay? So the rate of change of area is constant. That's Kepler's second law.
So how to define the first law if you want to define
Planets, yeah, planets rotate around a mass in a circular or elliptical orbit. Circular, as in the adjective for circle.
The moon has an elliptical.
No, you give me your sentence. Planets go around, masses go around other masses in circular or elliptical orbits. Or you can, let me simplify it more. No, I'll simplify it even more. Orbits are circular or elliptical. Well,
But our moon has an elliptical orbit.
I'd say it's more closer to a circle than an ellipse. The Earth would be pretty elliptical. Okay? Get up. Don't do this in my class. You two talk. Come on.
I'm here, I'm okay.
Sit up.
So
please.
orbits are circular or elliptical.
Yes. Alright, and then Kepler's third law, I gave it to you.
Yeah.
So you have his three laws. Which do they do in the exam? The third one. Okay? I have not seen the first one, I have not seen the second one in the exam. They could still ask it, I just haven't seen it. Alright, let's do some questions now. Actually, a little bit more vocabulary before I forget. Can I scroll down? Yeah. So, Earth, and then this is a GPS satellite. You know GPS, right?
No.
Good. Okay. There's two words here. Geostationary or parking orbit. So you can use this word or this word. Does anybody know what that word means? Geostationary or parking orbit?
Is it
No.
near enough to rotate around the Earth
No.
without?
Now, let's just break it down for a moment, okay?
Geo is
What? Yeah, geo is Earth. And stationary?
station.
Not moving. But of course it is moving around the Earth.
Oh, so it doesn't change the orbit.
Not this, good guess though.
Same distance from center of Earth to the.
True, but also not this, but we're getting there.
Is that the orbit within?
Now, I'll tell you, okay? Geostationary means for Earth that the satellite time to go around the Earth is 24 hours. Now, how long does it take the Earth to turn? 24 hours. No, sorry, I just meant so 24 hours. So if the satellite takes 24 hours as well, that means it always looks like the satellite is above your head. Because as you move around, so does the satellite. So to a person on the Earth, you know, let's say here, how long does it take them to go around? 24 hours. And then the satellite, 24 hours. So it always looks like it is above the person. I have seen this word in the exam many times. They have said geostationary orbit or parking orbit. So in this case, what it means is the t equals 24 hours, basically. That's what it means. Now write that down, okay? So this is geostationary or parking orbit. Okay. Right. So I'll do an example of that in a moment, but we all know this word now, geostationary or parking orbit, okay? There's one last formula to give you. It's a simple one, I haven't given it to you yet. We have the formula omega equals theta over t, okay? So if I'm talking about one cycle, that means that theta equals 360 degrees, or in other words 6.28 radians, or in other words 2 pi radians. So I can say omega equals 2 pi over big T. So if I call big T the time for one cycle, there's a special word for that, you had it, period time or periodic time. We have this formula now. We can say big T equals 2 pi over omega. Or, another way of saying it is that omega is 2 pi over T. That's important for the exam because usually in the exam they give you the T and you need the omega for the calculations, or they give you the omega and you need the T. So my point I'm making is if they give you omega, it's easy to get the T, and vice versa. If they give you the periodic time, no problem, you can easily get the omega. So it's almost like giving you the same thing. Okay. Right. Next example. Okay. Can I scroll down? Yeah? All right. Here is mass m, and it's on the Earth, and the Earth has radius, the Earth has mass of 5.98 times 10 to the 24 kilograms.
Is the center is the Earth?
Yeah.
And what about the red boundary?
That's the surface. Yeah, sorry. Yeah, sorry. Surface of the Earth. Tell me, how could I calculate the mass of the Earth? Using Kepler's third law. Now I'm going to calculate the radius of the Earth. The radius. Not quite, but something similar. So let's look at this one. So here I want the ore. Okay. So what force is pulling down on this? Yeah, gravity. So F equals G m over r squared. So you have F equals 6.67 times 10 to the minus 11 times m. times 5.98 times 10 to the 24 all over r squared. Can somebody please multiply those four numbers together?
That's 3.98886.
3.98
Yes, times 10 to the power 14.
times 10 to the 14 m over r squared. Great. But somebody said a moment ago that this here is also the weight. And what is the formula for weight when you're on the surface of the earth? mg. So you now have this result. mg equals 3.98 times 10 to the 14 m over r squared. Well, what happens to the m's? They cancel. And now you're left with this. R equals square root 3.98 times 10 to the 14 over 9.81. And what's that? Give it as scientific, the 6 with a point.
6.4 times 10 is
Meters. Yeah. Oops. Now please be very careful. That formula, weight equals mg, you can only use that formula when you are on the surface of the earth. No other situation. That's why I was allowed to use it. But Newton's formula, the F equals g mm over r squared, you can always use that. Always. Okay? So this one here, always. But this one here, only sometimes.
So why is that sometimes?
The formula is only for, well, think about it, that formula is only when you're on the surface of the earth, because if you're in deep space, what's your weight? Zero. But you still have a mass, so you can't use the formula. So it's only for the surface of the earth. Because that's the only time that you have this particular weight. And in fact, you could prove that formula using Newton's formula there, the F equals g mm over r squared. You could prove it, but we won't do that. Or you can do it at home if you want. Or I can do it next time. Yes? Let me do the time. Oh, plenty of time. Plenty of time. Let's have a look here. What day is today? Wednesday. So, homework questions, which you can start now. Go to page 70. Yep, 70. I'm always serious. No, don't do this. It sounds like a cartoon in here.
Up to 17.
Is it in Friday?
Tuesday.
No, I'll tell you what. We need to do this a bit sensibly. Yeah, let me think.
That's true.
Let me think.
Take your time.
How many are there? 1, 2, 3, 4, 5,
Second.
6, 7, 8. Also, you see, I also want to do some revision before your mid-semester exam. We have next week and then the exam after the holiday. So we have a class. Huh? No, but it's still good.
It's
Yeah.
still the sound.
Yeah. So we have one class tomorrow, or one double class tomorrow, 3 double classes next week. That's 4 double classes. So I would like to leave some time to do a revision class, and I have mechanical oscillations as one chapter, and then I have energy and its uses. So that's 1, 2, 3. So that's all of next week accounted for. Good. Okay. So what I'll do is you can start them now, but for homework, try to get the first half, the first 4 done. And then tomorrow in class, we'll have half the class time to finish this. And then the other half of the class, we can either do a tutorial if you need to see these, or if you're okay, we can then start the next chapter. And then if we start the next chapter this week instead of next week, we have a little bit more revision time next week.
Sure.
Okay, so you can do 10, 11, 12, 13 tonight, and you can start them now, and then tomorrow we'll do half a class on finishing those questions. Now, if you want to finish them all tonight, I'm happy with this. I have no problem with this. But as a minimum, the first 4. Okay, so if you can work on those now. Yep. Yep. Can I close this here?
Yeah.
Yeah.